Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at power inverters to understand the basics of how they work and where we use them. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. A typical inverter looks something like this. It has some red and black DC terminals on the back end, and on the front end we find some AC electrical outlets. That's because there are two types of electricity. There is AC and there is DC. An inverter is used to convert DC, or direct current, into AC alternating current. We can also convert AC into DC with the use of a rectifier, but we'll cover that in a separate video, and I'll leave some links in the video description down below for that. The appliances in our homes are designed to run off of an AC supply, and they get that from the electrical outlets which all provide AC electricity. However, electricity produced by things such as solar panels and batteries produce DC electricity. So, if we want to power our electrical devices from renewable sources, battery banks, or even our car, then we need to convert DC electricity into AC electricity, and we do that with an inverter. Where have you seen inverters used, or where would you like to use one? Let me know your thoughts and your project ideas in the comment section down below. To understand how an inverter works, we first need to understand some fundamentals of electricity. Inside a copper wire, we find copper atoms. These have electrons which can move to other atoms. These are known as free electrons because they are free to move around. They will randomly move in all directions, but this isn't of any use to us. We need lots of electrons to move in the same direction, and we do that by applying a voltage difference across the wire. The voltage is like pressure and will push the electrons. When we connect a wire to the positive and the negative terminals of a battery, we complete the circuit and electrons begin to flow. We call this flow of electrons current. The electrons always try to get back to their source. So if we place things such as lamps in the path of the electrons, they will have to pass through this, and they will therefore do work for us, such as illuminating this lamp. The electricity from solar panels and batteries is known as DC electricity, and that's because this type of electricity flows in just one single direction. It flows from one terminal directly to the other terminal. If we reverse the battery, the electrons flow in the opposite direction. You can think of DC electricity like a river, with the current of water flowing in just a single direction. Now in these animations I use electron flow, which is from negative to positive. But you might be used to seeing conventional current, which is from positive to negative. Electron flow is what's actually occurring. Conventional current was the original theory, and it's still widely taught today. Just be aware of the two and which one we're using. When we use an oscilloscope to look at the electrical waveform for DC, we get this flat line at the maximum voltage in the positive region. If we were to cut the power, then the line will drop to zero. If we turn the power on and off repeatedly, then we get a square wave pattern between 0 and maximum. But if we were to pulse the switch to open and close over different lengths of time, then we would get a pulsating pattern. With AC electricity, the electrons alternate by flowing forwards and backwards constantly. That's how it gets its name, because the current of electrons alternates in direction. You can think of this type of electricity like the tide of the sea. It constantly flows in and out between the maximums of high tide and low tide. If we followed the copper wires back to the generator, the wires are connected to some coils of wire which sit within the generator. Inside a basic generator, we also find a magnet at the center which is rotating. The magnet has a north and south pole, or you can think of it as a positive and a negative half. The electrons in the wire are negatively charged. As you might already know, magnets push or pull depending on the polarity. So as the magnets rotate past the coils, the positive and the negative half are going to therefore push and pull the electrons within the copper coils and also through the connected copper wires. The magnetic field of the magnet varies in intensity. So as the magnet rotates past the coil will experience a change in intensity of the magnetic field. This will be from 0 up to its maximum intensity, and then as it passes the coil, it will decrease again back to 0. Then the negative half comes in and pulls the electrons backwards with the same change in intensity. Each full rotation of the magnet will therefore produce this wave pattern known as a sine wave. The voltage is not constant in this type of electricity. Instead, it repeatedly moves from 0 up to its peak, back to 0, then to the negative peak, and then finally back to 0 again. Frequency refers to how many times this AC sine wave repeats per second. In North America and a few other parts of the world, we find 60 Hz electricity, which means the sine wave repeats 60 times per second. And as each wave has a positive and a negative half, this means its polarity will therefore reverse 120 times per second. In the rest of the world, we mostly find 50 Hz electricity. So the sine wave repeats 50 times per second, and therefore the current reverses 100 times per second. The inverter consists of a number of electronic switches known as IGBTs. The opening and closing of the switches is controlled by a controller. These can open and close super fast in pairs to control the flow of electricity. By controlling the path which the electricity takes, and how long it flows in the different paths, we can produce AC electricity from the DC source. I'm going to animate these using some simple switches to make them easier to visualize. Remember, AC is where the current reverses direction. We saw earlier in the video that we can reverse the direction of current by reversing the battery. We could very quickly reverse the battery to produce a rough AC supply. But an easier way would be to connect 4 switches or IGBTs across our load, such as a lamp. If we open and close these in pairs, then we can produce AC electricity. So, if we were to close switches 1 and 4, then the current flows in one direction. And if we then open these and close switches 2 and 3, we get current flowing in the other direction. So we can use the controller to automatically do this again and again and again. If we did that 120 times per second, then we would get 60 Hz electricity. And if we did that 100 times per second, then we would get 50 Hz electricity. As we have a low voltage input, we're going to get a low voltage output. To reach the 120 volts or 230 volts required to power our appliances, we will also need a transformer to step up the voltage to a useful level. When we look at this through an oscilloscope, we get a square wave in the positive and the negative regions. This is theoretically AC because it reverses direction. But it doesn't really look much like an AC sine wave, so how can we improve this? Do you remember earlier in the video when I said we can open and close the switch at different speeds and durations to change the waveform? Well, we can do that for this too. What we do is to use a controller to rapidly open and close the switches multiple times per cycle in a pulsating pattern, each pulse varying in width. This is known as pulse width modulation. The cycle is broken up into multiple smaller segments. Each segment has a total amount of current that could flow. But by rapidly pulsating the switches, we control the amount of flow occurring per segment. This will result in an average current per segment, which we see increases and decreases, thus giving us a wave. The load will therefore experience a sine wave. The more segments we have, then the closer it mimics a smooth wave. We can control the output voltage by controlling how long the switches are closed for. So we could, for example, output 240 volts or 120 volts just by trimming the opening and closing times. We can also control the frequency by controlling the timing of the switches. So we could, for example, output 60 Hz, 50 Hz, or 30 Hz, whatever is needed for the application. So that's how we can take a 12-volt DC battery and convert this into a 120 volts or 230 volts AC supply by using some IGBTs, pulse width modulation, and a transformer. But what if we needed more power? We also have single-phase as well as three-phase AC electricity. Most homes around the world use single-phase electricity. Large commercial buildings, as well as some homes, especially in Europe, will use three-phase electricity. Homes in North America use split-phase electricity, where a center tap transformer splits a single phase into two, which provides two hot wires and a neutral. We've covered how split phase electricity works in detail in our previous video. Do check that out, links down below. With single phase, we have a connection to just a single phase from a generator, so we have just one sine wave. But with three-phase electricity, we have a connection to each of the three phases. The phases are coils of wire which are inserted into the generator 120 degrees apart from the previous. This means the coils experience the peak of the rotating magnetic field at different times. And it's this that gives us our three phases, each with a different sine wave that is slightly out of sync from the previous. Remember, electricity wants to get back to its source in a complete circuit. As the current is flowing forwards and backwards at different times in each of the phases, we can essentially connect the phases together and the current will move between the different phases as the polarity of each phase moves forwards and backwards at different times. Any excess will flow in the neutral back to the source if needed, but that's only if the load on any of the phases is unbalanced. With single phase, we have these large gaps between the peaks. But with three phase, these can be combined to fill in the gaps and therefore deliver more power. Larger applications require a three-phase inverter, for example to run the compressors in a large cooling system. The DC supply in this case will be a rectified three-phase AC supply. That means the three AC sine waves are combined together and pass through some diodes which prevent the electrons from flowing backwards. This turns it into a rippled DC waveform. We then use a capacitor to smooth the ripple out into a constant DC supply. Now we have covered this in great detail previously, do check that out, links down below. To turn the clean DC into three-phase AC, we use a three-phase inverter. For this we use 6 IGBTs. Again, I'll animate these as simple switches for simplicity and I'll also number these as follows. To get our three phases, we need to open and close switches in pairs to direct the flow of current to form our supply and return paths. That way the connected motor will experience alternating current. For the three-phase supply, we time the switches to simulate the three phases. Let's see how this works. First, we close switches 1 and 6. This will give us phase 1 to phase 2. Then we close switches 1 and 2. This will give us phase 1 to phase 3. Then we close switches 3 and 2. This will give us phase 2 and phase 3. Then we close switches 3 and 4. This will give us phase 2 and phase 1. Then we close switches 5 and 4. This will give us phase 3 and phase 1. Then we close switches 5 and 6, and this will give us phase 3 and phase 2. This cycle repeats again and again like so. If we check this with an oscilloscope, we now have a wave pattern that looks something like AC, except it's still a little bit square. This will work fine for some applications, but not all. So again, we need to use pulse width modulation to create the sine wave. So we're going to use the controller to rapidly open and close the switches to vary the output frequency and voltage, and that way we get our three-phase AC supply. Okay guys, that's it for this video, but to continue your learning then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, LinkedIn, Instagram as well as theengineeringmindset.com.